The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, today we're going to go on to section 11.2, which has to do with inverse functions, and we'll get there eventually. So let's start out with the following. We've talked about equations. We've talked about functions, that a function is an equation where each input goes to exactly one output. So you can have several inputs going to the same output, but you can't have one input going to more than one output. Well, today we're going to talk about one-to-one functions. A one-to-one function, and I'm going to read this from the book, what it says here. A function is called a one-to-one function if different inputs determine different outputs. In other words, with a one-to-one function, not only does each input go to exactly one output, but each output comes from exactly one input. So you can't have several inputs going to the same output, okay, for it to be a one-to-one function. And let's look at some sort of mappings of that. Let's say we had the following. We've got 2, 3, 7, and 10. And here we've got 9, 4, and 3. And 2 goes to 9, 3 goes to 4, 7 goes to 4, and 10 goes to 3. This is a function, but it's not one-to-one because you've got more than one input going to the same output, okay? How about this situation? 1, 2, 3, 4, 5, 6, 7, 8. 1 goes to 5, 2 goes to 7, 3 goes to 6, and 4 goes to 8. This is one-to-one. For each input, there's exactly one output, and for each output, there's exactly one input, okay? Now, we've talked in the past about the vertical line test. Let's see here. For instance, if I had this graph, it passes the vertical line test. So it's a function. Whereas, let's see, this fails the vertical line test, so it's not a function. Well, for a function to be one-to-one, not only does it have to pass the vertical line test, but it must also pass the horizontal line test. So this linear equation, linear function, is in fact a one-to-one function. Let's see here. Is this a one-to-one function? Well, it passes the vertical line test and the horizontal line test. So yes, it is. Let's see here. Is this a one-to-one function? It passes the vertical line test, but it fails the horizontal line test. So not 1, 2, 1. Okay, let's see. How about this one? It passes the vertical line test and the horizontal line test. So yes, it's one-to-one. And how about that one? Yes, it's a function, but no, it's not one-to-one. It fails the horizontal line test. Okay, now, if a function is one-to-one, it has what's called an inverse function. And the best example of that I can think of is converting from Fahrenheit to Celsius, and then converting from Celsius back to Fahrenheit. So if the Fahrenheit formula is the original function, the Celsius formula would be the inverse function. Let's see here. If a function is one-to-one, and going from here to here is the function. Coming back would be the inverse function. Now, notation. Function notation looks like that. Inverse function notation, it looks like f to the -1 power, which you might think means this. And no, that's not what that means. That's an inverse function of that. Now, there are several things true about inverse functions, and we're going to go through all of them today. One is that an ordered pair in a one-to-one function, let's say you've got f of x, and one of the ordered pairs is 3, -4, okay? Well, then for the inverse function, one of the ordered pairs would be -4, 3, because all of the ordered pairs, their x and y values would switch if you have a function and then its inverse. If you graph a function and its inverse, a one-to-one function and its inverse, on a graph, they're symmetric about the line y equals x. And let's see, also, if you compose f of x with f inverse of x, I guess it should look like this. And then you compose f inverse of x with f of x. If you compose it in both directions, you should get the same answer, as we will see. I talked yesterday about how, let's see, composition was not commutative in general. However, in the case of a one-to-one function and its inverse, they are commutative. And let's see what else. Oh, there's a way to algebraically find a inverse function of a one-to-one function. All right, I just kind of threw that all out there. We're going to come back and look at it a piece at a time. We've already talked about the whole idea of the vertical and then the horizontal line test. What I want to do now is take a function, f of x equals 2x plus 4. That is a one-to-one function. So this is a one-to-one function. And I'm going to go through a 4-step process to find its inverse function. Okay, so the first step is to rewrite the function, but change the f of x function notation to just y. So the first step, replace f of x with y. Okay. The second step, interchange all the x's with all the y's in that original equation. So we get that. The third step is to solve that new equation for y. So I'm going to subtract 4 from both sides and divide both sides by 2. I'm going to rewrite it using putting y on the left side of the equation. That's not really an official step. It's just I like to have it that way. And then the fourth step is to replace y with f inverse of x notation. Now, you could write this function this way, or you could also write it like that. Okay, for graphing, this is probably the preferred method, but it's equivalent to that and equivalent to that. So again, the 4 steps: take the original function, the one-to-one function, replace f of x with y, interchange x and y, solve the new equation for y, replace y with f inverse of x notation. Any questions on this particular example? All right, let's take a look. Let me see here. I'm going to write these down. F of x is 2x plus 4, and f inverse of x is 1/2 x minus 2. All right, so let's take a look at these again. F of x equals 2x plus 4. F inverse of x equals 1/2 x minus 2. Let's find some ordered pairs for f of x. How about -1, 0, 1, and 2? Okay. If x is -1, f of -1 would be 2 times -1 plus 4, which is -2 plus 4, which is 2. If x is 0, f of 0 is 2 times 0 plus 4, which is 0 plus 4, which is 4. If x is 1, f of 1 equals 2 times 1 plus 4, which is 2 plus 4, which is 6. And if x is 2, f of 2 equals 2 times 2 plus 4, which is 4 plus 4, which is 8. All right, any questions about that? All right, let's find some ordered pairs for the inverse function. And for my inputs, I'm going to choose 2, 4, 6, and 8. Okay. If x is 2, f inverse of 2 is 1/2 times 2 minus 2, which is 1 minus 2, which is -1. If x is 4, f inverse of 4 is 1/2 times 4 minus 2, which is 2 minus 2, which is 0. If x is 6, f inverse of 6 is 1/2 times 6 minus 2, which is 3 minus 2, or 1. And if x is 8, f of 8 equals 1/2 times 8 minus 2, which is 4 minus 2, or 2. Notice, as I mentioned briefly earlier, that for the inverse function, all of the ordered pairs, the x's and y's are switched. Now, that should make sense because if you think about it, when we found the inverse function right here, what did we do? We switched all the x's and the y's, okay? So an ordered pair of the one-to-one function, the x and y would get switched for the inverse function. Any questions about that? All right, let me copy this down. -1, 0, 1, 2, 8, 6, 4, 2, and 2, -1, 4, 0, 6, 1, 8, 2. All right, now, I said that the graph of a one-to-one function and its inverse function, which is also one-to-one, by the way, the two graphs are symmetric about the line y equals x. So first of all, let's see, let's take f of x equals 2x plus 4, and I'm going to recopy the table values. I had -1, 2, 0, 4, 1, 6, and 2, 8. And then the f inverse of x function, we had 2, -1, 4, 0, 6, 1, and 8, 2. In fact, let's make this one in red. So the f of x, let's see, -1, 2, 0, 4, 1, 6, 2, 8. It's off the graph, so we'll just go with what we've got. And let's see here. I'm going to graph that. I'm going to get that picture. Okay. Now, let's do the inverse function in red. Let's see, x is 2, y is -1. Is that right? 2, -1, 4, 0, 6, 1, and 8, 2 again isn't on the graph. And let's see here. There's the inverse. So This is f of x, and this is f inverse of x. Okay, now I said that they were symmetric with each other about the line y equals x. What does that look like? Well, let's see, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, etc. And see here. So there's the line y equals x. Are the black and the red lines symmetric about the line y equals x? Yes, they are. Okay. Any questions about that? All right. Now, I also said that a one-to-one function and its inverse, if we apply composition to them, we should get the same answer whether we do f composed with f inverse of x or f inverse composed with f of x. So we're going to compose both of them and see what happens. All right, so f of x is 2x plus 4. F inverse of x is 1/2 x minus 2. Okay. So I'm going to find f composed with f inverse of x. So that's f of f inverse of x. Well, f inverse of x is 1/2 x minus 2. So that's going to go in there. And we're going to have f of 1/2 x minus 2, which now that goes in there. So that's going to be 2 times the quantity 1/2 x minus 2 plus 4, which is x minus 4 plus 4, which is x. So f composed with f inverse of x equals x. Any question about what I just did there using composition? Okay, now let's take f inverse composed with f of x and see what we get. Well, that's equal to f inverse of f of x, which is f inverse of, let's see, f of x is all of that. So all of that is going to go in here. And that's going to be 1/2 times 2x plus 4 minus 2, which is x, plus 2 minus 2, which is x. So f inverse composed with f of x also equals x. So composing two functions, a one-to-one function and its inverse, composing them in both directions, you should get x. Likewise, if composing two functions in both directions yields x, those two functions are inverses of each other. All right. Any questions about that? So I've done everything with these two functions that I talked about earlier. Let's see here. We took the one-to-one function f of x, we found its inverse using 4 steps. We graphed, let's see here. We found ordered pairs and saw that an ordered pair for f of x, if you inverted x and y, you got, or inversed, reversed, switched them around, you got an ordered pair in f inverse of x. And we looked at the graph of it to see that they're symmetric about the line y equals x. And we composed them in both directions to get x. All right. Now, second here, I want to point out another piece of information, and perhaps looking at this is the best way to do that. The domain of a one-to-one function is the range of the inverse function. The range of a one-to-one function is the domain of the inverse function. So just like the x and y switch, the domain and the range switch. Okay, any questions about that yet? All right, so let's take a look now at, actually what I'm going to do, I'm going to close this up and open it up again so that I have a bunch of clear graphs to use here in just a bit. Let's take, let's see here. The directions say, find the inverse of each function, then graph the function and its inverse on one coordinate system. Show the line of symmetry on the graph. Okay, and I'll go through all that again. So let's say we've got this. We've got f of x equals x squared plus 1. And then it says x is greater than or equal to 0. Okay. So if this is a one-to-one function, finding its inverse, let's see, y equals x squared plus 1. So we are replacing f of x with y. Okay. Then we're going to interchange x and y. So at that point, now it's the inverse. Okay. Then we're going to solve for y. So I'll subtract 1 from both sides. I'm going to go ahead and switch around the sides so that my y stuff is on the left. Well, now to solve for y, I would take the square root of both sides. So y is plus or minus the square root of x minus 1. And then finally, using inverse function notation, I get that. All right, if you're taking notes, I hope you're using pencil and not pen, because there's some problems here we're going to look at. Something wrong with this situation. Okay, now let's graph our original function. Okay, f of x equals x squared plus 1. Wouldn't that be 2, 4? Wouldn't that look like this? It'd be a parabola. It's basically y equals x squared, but moved up 1 unit. So that is f of x equals x squared plus 1. Okay. Is that a one-to-one function? Anybody?
No.
Why not? How do you know for sure?
It doesn't pass horizontal line test.
Correct. It doesn't pass the horizontal line test. Well, let's go back and let's look at the actual function. Oh, look here. There was a restriction. It said x is greater than or equal to 0. So let's apply that restriction to this graph. If x is greater than or equal to 0, then that's what our graph would look like, isn't it? So here, let's apply this. X is greater than or equal to 0. So basically, by taking a function and doing some genetic engineering, so to speak, by putting a restriction on the domain, we create a one-to-one function. So far, so good? Okay.
Yeah.
Now, let's take the inverse function. Let's see, f inverse of x equals plus or minus the square root of, okay, so let's see here. F inverse of x equals plus or minus the square root of, is it x, x minus 1, okay. So that's what I had for the inverse function, okay? If I graphed that, basically it would look like that, okay? And I could go through the process, but this at the moment, just kind of take my word for it. But that's supposed to look like the reflection of this through the line y equals x. So what would we have to get rid of here?
The negatives?
Yeah, we'd have to get rid of this piece down here, right? Which would be getting rid of this piece. Whoops. So keep this in mind. Remember when I said the domain of the one-to-one function is the range of its inverse, including restrictions. So on the original function, x has to be greater than or equal to 0, which means on the inverse, y has to be greater than or equal to 0. Well, if y is greater than or equal to 0, that would get rid of the negative and get rid of this piece that I had there a minute ago, this thing down here, okay? So my point is, it all fits together. It all makes sense, hopefully. So now we've got a one-to-one function and its inverse. The restriction we applied here to x is a restriction we apply here to y. You all right with that? Any questions there? Okay. And what I want to do now is focus on solving, finding the inverse of a one-to-one function. That tends to be the thing that gives people the most trouble. So I'm going to just look at some more examples. Here we have f of x equals 2x plus 6 all over 3. And we are told that this is a one-to-one function. So step number 1, replace f of x with y. Step number 2, interchange x and y. Step number 3, erase it and write it so that it's legible. Yeah. Step number 3, solve for y. So I'm going to multiply both sides by 3. 3x equals 2y plus 6. Then I'm going to subtract 6. 3x minus 6 equals 2y. I'm going to divide by 2. 3x minus 6 over 2 equals y. I'm going to switch it around. And then I'm going to replace y with f inverse of x. And again, you could write it that way, or you could write it like that. So here's the original function. Here's its inverse. Okay. Now, it isn't wrong to leave it like that, but since it's a linear equation, it just seems like it makes better sense to put it in slope-intercept form, okay? One of the things that people will forget to do is this last step, introducing the inverse function notation. So just be careful that you go through the 4-step process. So step number 1, replace f of x with y. Step number 2, interchange x and y. Step number 3, solve for y. Step number 4, replace y with f inverse of x. Any questions about this particular example? All right, let's take a look at another one then. F of x equals x cubed minus 4. So we're going to find the inverse of this one-to-one function. Step number 1, replace f of x with y. Step number 2, interchange x and y. Step number 3, solve for y. Oops. Don't forget, when you take a square or a fourth or basically an even root, you get the plus or minus, but with an odd root, you don't get that. You just get the 1 result. So there's step 3, solving for y, and then step 4, using f inverse of x notation. Any questions about that? Okay. Let's take a look at this one. This is a one-to-one function. So step number 1, replace y, or excuse me, replace f of x with y. Step number 2, interchange x and y. Step number 3, solve for y. So I'll multiply both sides by y. I get yx equals 1. Divide by x, and I get y equals 1 over x. Step number 4, replace y with f inverse of x. Back in the day, I used to love to put this question on a Math 141 test to see if students really knew what they were doing. It's kind of a mean question because in this case, the function and its inverse are the exact same function. Why is that true? Well, let's take a look at this thing. Oops. Let's see. Okay, so I've got f of x equals 1 over x, and then f inverse of x equals 1 over x. So I'm saying that the function and its inverse are the same. Let's find some ordered pairs. That looks like a 4 and it's supposed to be an x. Okay, so let's see here. If x is 1, y would be 1. If x is 2, y would be 1/2. If x is 3, y would be 1/3. What if x is -1? Y would be -1. What if x is -2? Y would be -1/2, and -3, y would be -1/3. Let's see what I get graphing that. 1, 1 is there. 2, 1/2 is there. 3, 1/3 is there. -1. -1 is there. -2, -1/2 is there. -3, -1/3 is there. So this little piece is going like this, and this little piece is going like that. What happens like right in here? Okay, well, how about if I let x be 1/2? Okay, if x is 1/2, f of 1/2 would be 1 over 1/2, which is 1 divided by 1/2, which is 1 times 2 over 1, which is 2. So when x is 1, y is 2. When x is 1/2, y is 2. Likewise, when x is -1/2, it would be -2. Well, what's going to happen if I keep plugging in numbers is I'm going to get that picture. Okay, so that's the graph of y equals, or f of x equals 1 over x. But let's draw the line y equals x. Can you see that this function in and of itself is symmetric about the line y equals x? Take a look at that piece. Isn't it symmetric about the line y equals x? And so is this. So its inverse would just be the whole thing. I mean, if you just took this thing and rotated it around the, well, if you rotated it around that y equals x axis, it would look the same, wouldn't it? I don't know if I'm convincing you or not, but so the reason that this one-to-one function and its inverse are the same is because the original function is already symmetric around the line y equals x. Anyway, that'll give you something to keep you awake at night. How about How are we doing for time? We got more time. Let's take a look at this. F of x equals the cube root of x minus 5. So finding its inverse, y equals the cube root of x minus 5. X equals the cube root of y minus 5. So now we're going to cube both sides. X cubed equals y minus 5. Add 5 to both sides. X cubed plus 5 equals y. Y equals x cubed plus 5. F inverse of x equals x cubed plus 5. So when the original was a cube root, we got a cube. A little while ago, I think I took one that was a cube and found its inverse to be a cube root. All right. So do you have any questions? Anything you want more examples of?
Not examples necessarily, but I was just curious, when we enter the inverse function notation, are we gonna have to enter that into WebAssign? And do we just do like the letter F and then a -1 exponent, or just
That is
curious?
an excellent question. And you know what? Nobody's ever asked me that before. So I'm going to look it up. So give me just a minute here. And let's see here. And I know you can't see what I'm doing yet. I just want to get to where I'm going and then I'll switch the screens. So student view. Get rid of that. Let's see, this is section 11.2. Okay. All right. So here is your assignment 11.2. Let's see here. Here they've already got it written. Here it's a selected. Here it's already written. It's already written. Okay. So far, so good. Yeah, this is what I was looking for. So here they're asking you to find the inverse function, but they're already giving you the notation. You see that on 16?
Yep, cool. Just
Okay.
making sure. Before
Yeah,
I
no,
got
that's a very good question. And like I said, nobody's ever asked it before. So I was like, well, I don't know. Let's take a look. Yeah, still.
It seems like one that it would definitely be picky about if you did it wrong.
Yeah. Okay, so the answer to your question is you don't need to worry about it. It's already
Thank you.
provided. You betcha. Anything else? Anybody? All right, well, I'm going to go ahead and stop the recording. I'll be back this afternoon at 1:15 with an office hour should you have need with me. Otherwise, I'll see you all tomorrow.